Have you ever seen an insect walk on walls and wonder, am I capable of doing that? Only to find out the hard way. What physical property allows such creatures to walk along very steeply inclined surfaces? To answer this question, naturally, as anyone would do, we visited a caterpillar in its own habitat and observed how a caterpillar can stand on a steep surface. Caterpillars, on average, have 8 Velcro-shaped prolegs that hook onto rough surface material. On stably inclined surfaces, caterpillars stop themselves from falling by applying a force through each of their legs in such a way to experience a net force of 0 acting on their bodies.
The prolegs hook onto rough surfaces. This means that the force applied by caterpillars pull on a surface, resulting in the surface pulling them back in the opposite direction.
Now that we know that insects have uniquely shaped legs which allow them to climb walls, we are able to measure on average how much force each leg exerts using Newton's law of inertia, expressed through free body diagrams.
A caterpillar crawling along the ground does not need a stabilizing force to keep it from falling. This is because there is a normal force acting directly in opposition to its gravitational force. However, a caterpillar walking on an inclined surface has a normal force acting on it at an angle relative to the gravitational force. To keep the caterpillar from falling, it needs to exert a force opposing both the normal and gravitational forces. A caterpillar climbing a tree would vertically have only its weight acting on it. This means the caterpillar exerts a total force equal in magnitude to the gravitational force acting on it. Why is there no forces acting horizontally on the caterpillar? The concept of a Velcro-shaped leg hooked onto a rough surface involves the idea that a hook exerts a force along a curved direction. And since a set of 2 prolegs hook onto a surface in opposite directions, the result is a horizontal net force of 0. Similarly, when a caterpillar walks on an upper surface, vertically only its weight acts on it, and needs to exert a total force equal in magnitude to its weight and opposite in direction to keep it from falling.
To help us in our calculations, we measured the mass of a caterpillar to be about 0.55 grams. On the ground, a caterpillar only experiences gravitational and normal forces acting on it. This means the total force applied by the caterpillar is 0. On a 45-degree inclined surface, by setting the axis to involve the normal force parallel to the y-axis, the caterpillar exerts a force equal to the horizontal component of the gravitational force. On a 90-degree inclined surface, in order for the caterpillar to not fall, it exerts a force equal in magnitude to its gravitational force. Similarly, on a 180-degree inclined surface, the force keeping the caterpillar from falling is equal to the gravitational force acting on it. These forces applied by the caterpillar is the average force applied by its 8 prolegs. So on the 45-degree incline, each of the caterpillar's legs apply a force of only 4.8 times 10 to the negative 4 newtons. And on both 90-degree and 180-degree inclines, each leg applies an average force of 6.75 times 10 to the negative 4 newtons.
So why can't us humans walk on walls? Well, in order for any creature to walk on walls, one must be capable of exerting a pulling force on a spot of a wall. Think of indoor rock climbing. By pulling on fixed rocks along the wall, we are capable of exerting a pulling force, allowing us to climb to the top. In the case of an insect like caterpillars, they create these fixed spots on walls by hooking their prolegs onto a surface. They then can apply a force to walk on walls. This also explains why insects can't walk on smoother surfaces, as their hook-like leg has nothing to clamp on.
Useless.